So thanks for joining me to listen my so-called good stuff lectures regarding the electromagnetic waves. So in this lecture, I will be speaking about the transverse nature of electromagnetic radiation, and in the end, I will be showing how can we derive the charge conservation law based on the Maxwell's equations. And like I said, lots of good stuff on the way, I would say. This chapter 4, I guess, needless to say, is my favorite lecture series in our course. So that's why I'm smiling all the time I'm lecturing and giving these lectures. So what we will be doing here is that I will derive a few of the fundamental properties associated with electromagnetic radiation. And here, for conceptual clarity, and this is also the way, the smart way of dealing with the mathematics, is that I will derive these properties for a time harmonic plane wave. So this might seem like not much to say, but this is in fact very important, and you should remember this in all of these lectures and all of the upcoming minutes I will be speaking. So I will be, and these laws, the properties that we will derive for the electromagnetic radiation, they apply for a single time harmonic plane wave component. So when you have actually something that is not a single time harmonic plane wave component anymore, it might be that these laws do not strictly anymore hold. So for example, the fact when we say that electromagnetic radiation is a transverse wave, that strictly applies only to a plane wave. But if we would form a more physical quantity using several plane waves, it might be the case that the electromagnetic field distribution inside this kind of radiation would not be entirely transverse anymore. So please be warned that these properties that we say, they are more like a kind of mathematical structure framework that is associated with the electrodynamics and electromagnetic fields, but they are not the whole truth. But you also need to be knowledgeable enough to apply them properly to really get the right kind of physical picture when we go into more complicated scenarios. So arbitrary electromagnetic waves, disturbances, for example, ultra-short laser pulses or tightly focused laser beams, we can always describe them as a superpositions of several time harmonic plane waves. So this we will be speaking more about in chapter 7 regarding the superposition, and these kind of tricks that we do mathematically, they are based on Fourier synthesis and analysis. So that's how we could generalize our treatment. But here, this is an introductory course. We do not really deal much with Fourier transforms, but we'll rather just be happy showing you the fundamental properties, and that's it. But really, if you would need to go to the more complicated picture, please, you would need to know how you Fourier transform things and how do you operate then subsequently with your piece of mathematics. But for example, in case of ultra-short pulses, we would have several time harmonic waves forming our pulses. And in the case of tightly focused laser beams, we would have several plane wave components forming our focus of a laser beam. And here in this case, when we would be tightly focusing the laser beam, this condition of electromagnetic field being transverse, that does not strictly apply anymore. And that's what I was referring to, that you have to be careful depending on the actual physical situation you're interested in looking into. So we will be looking into time harmonic electromagnetic fields. So of course we should consider fields that are of specific form. So let's look into the electric fields that are time harmonic plane waves. So we have the amplitude in principle that can depend on position, and then we have the time harmonic contribution here. So it oscillates harmonically with respect to time at the specific frequency of omega, and that's the angular frequency. And since we specify that we want to deal with plane waves, then our, in principle, spatially dependent amplitude is actually a constant, and it has the structure of a plane wave. So then we have an amplitude E0 vector, that's the amplitude vector, the polarization of light, And then we have the plane wave component here, exponent IKR, that ensures that I have a plane wave. And then I'm multiplying this with the time harmonic time dependence. So this is the form for the E field and B field I will be considering in what follows. And now I know that this plane wave component propagates along the direction of the wave vector k, and it oscillates with the angular frequency of omega. And if we are propagating in vacuum, the divergence of the electric field vanishes. So in other words of saying, electric field is solenoidal field. And what this means is that the divergence of the E field equals 0. We could also just say that if you're interested only in propagation, here we don't have sources, we don't have electric charges, we don't have currents, and subsequently the Maxwell's equations give us this. And here, this is a little bit of a jump, but you will verify this jump to yourself at the homework exercises. So if I'm calculating the divergence of the E field, so I'm basically operating with a nabla dot on the E field, and when the E field is time harmonic plane wave, I can actually replace this operation by just calculating the dot product of k, the wave vector, with the E naught. And this is equal to 0. So what we can come up with this is that we can write the k dot E like using the geometrical definition of the dot product, that it's the amplitudes of the two vectors. So it's the length of the k, the wave vector, and the length of the polarization E naught times the cosine with respect to these two vectors. And since I know that this must be equal to 0, and certainly the k, amplitude of k is not 0, and the polarization vector E naught is not 0, that implies to me that the theta angle must be 90 degrees. And of course this means that the E field is a transverse field, so that they graphically put k and E are perpendicular to each other. So I have just discovered from here, based on the divergence of E being 0, that E and k are perpendicular to each other. What I will do next is that I will show that in fact all k, E, and B are mutually perpendicular to each other, and then like I will also say a little bit about the E and B fields oscillating in phase. So E field, of course, based on the Maxwell's equation. I'm now going too quickly. So the E field, of course, it was the time harmonic plane wave, this form that we started with, and this fulfills this condition. And since we know that the vector E naught, this is earlier was introduced as the polarization of light, we know that the direction along which this E field oscillates is transverse with respect to the k. And this is essentially a graphical picture that how we can understand things. So this E naught, this is the polarization of light, and then this plane in where this polarization of light oscillates and how it oscillates is always perpendicular to k. And the B field, often of the electromagnetic field, it behaves similarly, because recalling the Gauss's law for magnetism, the divergence of the B field is 0. So essentially I can already just say that the B field will also be perpendicular to the k, the wave vector. And next I will show that indeed EB fields are perpendicular also with respect to each other, so that they do actually propagate in the same direction. Which sounds like intuitively correct, but let's just verify that with the mathematics. So we start with the Maxwell-Faraday equation. So the curl of the E equals minus time derivative of B field. And now this equality also looks simple, and you will verify this using the homeworks. So essentially when I'm calculating a curl of a time harmonic plane wave, the operation is exactly equal, that I would be multiplying the E field with the I imaginary unit times the wave vector and the vector cross product of these. So essentially I can replace the nasty curl operator with the IK operator. And since I'm using the Maxwell-Faraday equation, I know that this equals to the minus partial time derivative of the B field. We can integrate this over time. since we are dealing with time harmonic plane waves. So now we know exactly how the E and B fields look like. And we end up with having an equality that we have -1/c times the unit wave vector k hat and the cross product with the E, and this equals to -b field. So I can simplify this slightly so that I can write this in a form that I have the unit wave vector k hat and the cross product with the E, and this equals to the speed of light c times the b field. And recalling the properties of the cross product, we now see that in fact all these vectors k, e, and b are mutually perpendicular. So we can now look into this. Okay, since we take the cross product, we know that the b field will be perpendicular to both of these, and that's what gives us the final conclusion that in fact, indeed, both E and B fields oscillate in the same plane, and this we could say that for a plane wave, time harmonic plane wave, indeed, electromagnetic radiation is transverse. So it's perpendicular with respect to the k vector. And we also notice from the math here that the E and B fields, they actually oscillate in phase. So this is also something that, especially in the high school material, somehow there seems to be confusion regarding the phases of the E and B fields. But looking here into the equations, we see that they actually are in the same phase. Maybe it's the Maxwell-Faraday, the curl, and the time derivative here that somehow the confusion arises from there. But definitely from here we see that there's no reason to say that they would not be oscillating in the same phase. Next, we will come up with a little bit more physical interpretation of the speed of light. So let's look into the derived equation. So we have the unit wave vector k hat, and we take the cross product with the E field, and this was equals to the speed of light c times the magnetic field. And k, of course, it's a unit vector, so its length is unity. And this basically tells us physically that the speed of light c gives us the ratio between the amplitudes of the fields of E and B. So essentially this tells that if I would want to calculate the amplitude of my magnetic field, I could just calculate that by calculating the amplitude of the electric field, and I would divide that with the speed of light. And this applies in general to plane waves in vacuum. And this is quite nice, because it's really connecting the amplitudes, the strengths of the fields, and the connection is taking place via the speed of light. So that's really a kind of a constant of nature in a way that it is somehow connecting the E and B fields together. And finally, like I promised in the motivation, I will show you that the conservation of charge, a very fundamental law, also follows directly from the Maxwell's equations. So I will start with Ampere's circuital law. So that's the fourth Maxwell's equation, and I will calculate the divergence of both sides. So this is the Ampere's circuital law. I'm calculating the curl of the B field, and that equals to the vacuum permeability, mu naught times J, the electric current density, plus mu naught times epsilon naught, the vacuum permittivity, times the partial time derivative of the E field. And I'm calculating the divergence of both sides of this Maxwell fourth equation. So I have, of course, on the left-hand side now that I'm calculating the divergence of a curl of B, and then on the right-hand side I have the mu naught, and then I'm calculating the divergence of the current density, and then I have the mu naught times epsilon naught times the time derivative of divergence of the E field. And please, now looking at the left-hand side, there's the identity. We're trying to calculate divergence of a curl, so that will be identically 0. So I can already simplify the left-hand side equation. And then on the right-hand side, I can take the mu naught, the vacuum permeability, to be a common factor. So what I have left is that I have the divergence of J. Then I'm summing that with the epsilon naught times time derivative of the divergence of E. And now, taking use of the first Maxwell's equations, the Gauss law for electricity, the divergence of E field equals to the charge density rho divided by the vacuum permittivity epsilon naught. So I can simplify the right hand side. So that's equal to the mu naught times the divergence of J plus time derivative of charge density rho. So this is what I have come up with by starting from the Ampere's circuital law, and I have also applied first Maxwell's equation. And this directly gives us the conservation of charge. So on the right hand side, I can take the two terms so that the divergence of J equals to the minus time derivative of the charge density, so that this equals to 0. And I can now, this is in differential form, I can transform this into the integral form. Maybe that gives you a better physical intuition what this actually implies and why its name is conservation of charge, so that I can calculate the divergence of my J with respect to some integration volume V. And then on this other side, I have minus volume integral over the time derivative of charge density. And of course, the V, the integration volume, is arbitrary. And I could now apply divergence theorem into this equation since I have the divergence of J. And I could transform this volume integral to be a area integral over a closed surface that encloses the volume V. And then I would calculate of how much current goes through the surface area elements dAs out of this enclosed surface. And physically, that would then mean that if I have an electric current flowing out or inwards of the enclosed surface, then that would be equal to a change in the charge densities into the time-dependent, giving a time-dependent charge density. So physically, that would tell us that if, for example, electrons move out from the volume, that manifests itself as a current, electric current. And at least in my mind, I can very easily imagine this to be very intuitively true, so that if electrons are moving away from this volume, I know that the electrons are going away, and that must be manifesting itself as a current. And vice versa. If I'm seeing a current going out from this volume, that must also mean that some of the electrons are not there anymore, or vice versa, that there will be more electrons inside this volume. So this is the kind of physical meaning of the conservation of charge. And in fact, we have even derived that from the Maxwell's equation, so that even know that it's in the structure of electrodynamics, this law. And finally, like I have it in my notes, that please also mention special theory of relativity. In case you're interested, of course, Maxwell's equations and the laws of electrodynamics, they are also fully compatible with the Einstein's special theory of relativity, so that this conservation of charge, if you know the formulation of electrodynamics, that is explicitly showing the compatibility with special theory of relativity. So we are then combining time coordinate with the three spatial coordinates. And mathematically, how do we do that? This kind of combination is that we start using so-called 4 vectors, so that we have vectors that actually have 4 components. One component is for time, and 3 components is for space. And the vector space that we are then dealing with is so-called Minkowski space, so that there's a specific type of connection between the time coordinate and the 3 spatial coordinates. But in this 4 vector notation, like this equality could be written very simply, because I could just calculate a divergence of my 4 vector for the electron, for J, and that would be 0. So the kind of mathematical structure would be even more elegant, and I would say even more transparent in terms of saying that we have this kind of law known as the conservation of law charge. But I admit myself that the kind of special theory of relativity in the context of electrodynamics, that's a little bit beyond our introductory course. But I just wanted to mention these to people, students who are interested to know more and going into the kind of most fundamental things that we can imagine about electrodynamics. And there I would say that one nice direction to go and try to learn would be to look into the theories of relativities and how do they manifest themselves in terms of electrodynamics. There's a lot of good connection points and kind of connections between electrodynamics and special theory of relativity and the general theory of relativity that really teaches us a lot about the structure of fields and also the structure of universe. So that's why I wanted to kind of nudge you slightly towards that direction in case you're interested. But of course, this is not our main message of this course. So this is only for if you're really interested, look into that. But I won't be asking about this in a homework or in an exam or discussion exercises. But I just wanted to mention this because I find it very elegant and beautiful myself. I'm kind of hopeful that others might also find it beautiful and elegant. But I thank you here. Thanks for listening my monologue. And in the next lecture, we will be looking more into the properties of electromagnetic fields, mainly of the energy associated with the EM field. So thank you for listening and bye-bye.